So significance testing is one of the more difficult ideas to wrap your head around in statistics. Executing one is not terribly difficult, but kind of understanding what goes on in the abstract here is a little bit more challenging. Essentially, you have a guess. Okay, you have a guess about some parameter. So in the abstract, we're just going to call that J. And you're going to guess that that parameter has some value. So J is equal to some value. And the second thing is you're going to make a counter guess that either J isn't that value, J is less than that value, or J is more than that value. Okay, so this is what we're going to call a two-tailed test, and these are going to be things that we call a one-tailed test. And in fact, these one-tailed tests are a little bit more intuitive than the two-tailed tests. We'll get into that in a minute. So what you're going to do is that once you've made this guess that J is this value, and you've made your counterclaim that, so this is what we're going to call the null hypothesis is your guess, and the alternate hypothesis is like the counter to that guess. Then you're going to collect some samples. So you're going to get a sample of a certain size, and you're going to get a point estimate for that parameter from that sample. And then what you're going to do is you're going to ask yourself this question. Okay, if J is the actual parameter, then what is the probability that I'm going to get that statistic or something more extreme? So in the left tail test, usually that statistic is below your guess, right? So usually that's below your guess. So if this were true, if the null hypothesis were true, what would be the probability that I would get a value, a statistic that was that or below? If it's a right-tailed test, then we would expect the statistic to be above my guess, which is like, what's the probability that I'm there? And then with the two-tail, it's one is the probability that I got that sample or something more extreme in both directions. So we're going to put some meat on this, and we're going to get something called a p-value. Okay, and the p-value is the probability that I'm in one of these tails. Okay, so the probability that if the null hypothesis is true, that I would get a sample like the one I got, or something more extreme in the direction of interest. Now, usually we test that against a level of significance, which is what we're going to call alpha. Okay, generally speaking, alpha is 0.05, but it can be different. But this gives you an idea of like to what degree is this finding statistically significant, right? So that's what we're going to come up with. So significance and confidence level have kind of an inverse reality. Something that is like when you're thinking of like confidence being like 95%, then significance is going to be 0.05. Okay, because the probability that it happened by chance is 0.05 if I'm 95% confident that what I'm doing is meaningful, right? So let's dress this up a little bit like a problem that might make some sense. So imagine that I'm like running a political campaign, okay? And like worst case scenario, I want my guy or gal or whoever to have at least 51% of the vote, right? So my guess, worst case scenario, is that my person has 51% of the vote. And I'm going to put as my alternate hypothesis here, the thing that I'm worried about, is that they don't. They have less than that. And now this is clearly a one-tailed test. Because if they have more than 51%, I'm fine. Things are great. And all of this, right? So my guess is that they have 51%, but I'm worried that they've got less than 51%. So what I do is I go and I take a sample. Let's say I take a sample of 500 people. And in that sample, right? In that sample, 240 of those people say they're voting for my person, which means that my P hat is 48%. It's not really good. Okay, it's a bad day for my candidate. So let's see how bad is that, right? So the question now is if my candidate actually had 51%, what is the probability that I would get a sample that had 48% or worse? In the area of that thing under this curve, this probability distribution is going to be what I call my p-value. Okay? And the probability there is actually 0.0898. So realistically, there's a 9% chance that my candidate could still have that 51% of the vote and get this 48% sample. Okay? So, like, this is worrisome, but it doesn't, like, put it that my guy definitely has less than 51%. All right? So let's say the next day I take another sample. So I grab another 500 people at random. And now I only get 235 guys. Nope, not 250. That would be half. 235 people voting for my candidate. So the percentage now just dropped to 47%. So let's think about this curve, right? So I'm still hoping that reality is that my guy's got a 51% share of the vote. And now I've dropped down to 47%. So that's going to make this area a little bit smaller. My p-value is now 0.0368. So I've dropped from an 8% chance of getting a sample of 48% or smaller down to a 3.6% chance of getting so I'm getting worse, right? My confidence in this is getting worse, right? This is actually not, this is like saying, like, warning, the probability that you would have got this sample and still had 51% is less than 5%. This sample is statistically significant to your campaign, and you better get your butt in gear, because you're not winning. Right, with that sample in play, the probability of you winning is like dropping precipitously, right? So this is, I think, the easiest way to see it is in a left tail test. Note, when we have a less than in the alternate hypothesis, we're shading less than our value, right? So let's take a look at let's maybe in a different light. So let's say that same situation, right? I still want my guy to have at least 51% of the vote, but I'm doing good. My polling is showing really good. So I want to make the alternate, like, whether or not he's got, whether or not he's got more than 51%. I'd like to think that that's what he's got. He's got more than 51%, right? So the question is like, what's the probability that I'm at 51% and not at more than, right? So now I'm going to go and take my sample. Right, so notice the alternate hypothesis working the other way. My sample's 500 people, right? Out of those 500, 270 say they're voting for my guy. So I'm feeling pretty confident here. I got like a sample, 54% in that sample said they're voting for my guy, right? So the question is like, if the true population is 51, which is, I need to be that or better, and I got a sample of 0.54. What's the probability that I would have got that sample or something better, given that the true proportion was 51%? And in fact, the p-value here is recognizable. It's 0.898. Because this is the exact same distance from the right as the bad sample was from before. Right? Earlier we were talking about 0.48 and gave me 8.9%. Now we've got 0.54 is 8.9% to the good, right? So the probability that I got this good of a sample and I'm at 51 is small, right? Which means that I got to be bigger than 51. Or there's a 9% chance that I would have done that, got that sample, and been at 51, right? So the question now is it's like, you know, this has got me feeling pretty good about things. But let's say the next day I go and I work the same hypothesis, right? Take the same sample size, 500 people, and this time I get only 260 are in favor of my guy, right? So my p-hat dropped from 0.54 down to 0.52. Right, so let's think about this. I'm still claiming that 51% is my guy's number. I got a sample that says 52. So what's the probability that I got that sample at 52 or something bigger? Right, this goes to like 0.32. Right, so that's got me a little nervous because, like, you know, I could have like right there at 51 or maybe slightly less, and I'm just like getting 32% chance of getting a sample that's as high as 52. So here, this is an example where I want P to be small because, like, I want my number to be statistically significant to say that I'm above 51. This is no longer statistically significant. It's saying, look, you might be at 51. You know, a 51 population has got a 32% chance of producing a 52. Like, that's not real strong evidence that you've got 51, right? So there's your one-tail test. Now, like, the two-tail test gets a little bit more convoluted, so we're going to take a look at that. So let's say I'm building a case for a laptop, right? And I believe that the mean width of a laptop is 13.5 inches. This is my claim. And whether I build the case too big or too small, I have a problem. So my alternate here is that the mean width of the laptop is not 13.5. It could be wrong in either direction. So I want to kind of go out and get a whole bunch of laptops. So I take a sampling of 50 different people's laptops, and I find that if I measure all 50 of them, the mean of that sample is 13 inches. And the standard deviation of that sample is 1.5 inches. So these are like the two parameters that I would need to know. Okay, so here's kind of what's going on here is that, like, if the true mean of the population was 13.5, what is the probability that I would get a sample like this one or more extreme? Well, this sample lands here at 13. So, like, what's the probability? So, but normally I'd say, okay, so great. What would be more extreme than that would be more to the left. But this could be more extreme in both directions. So how extreme is this? I'm off by 0.5 points, right? So being that extreme in the other direction puts me at 14.5. And see, the probability of being in this tail more extreme than 13 and going down, right? Like more than a half a unit off going down is this like 0.1125. And the probability of being more than a half a unit going up is also 0.01125. Right? So these two probabilities have to get added together for the two-tail test, which means my p-value, the probability of having a value more extreme than my statistic, is actually going to be 0.0225. So I have a 2.2% chance of finding a laptop that is more extreme, or that, sorry, that's not correct. There's a 2% chance that my estimate is more than 2.2%, 2.3% chance that my estimate is more than a half of an inch off from the actual mean of the laptop widths, right? I mean, yeah, it's easy to say I can find a laptop that's more than half an inch off, sure. But having the ability to have a sample of size 50 where the mean is more than a half of an inch off, right? If the actual mean is 13.5, that's where I'm down to like 2.2%. Okay, so this really means that chances are the mean size of the laptop isn't 13.5. This this statistic is saying that like there's a very small chance that that's really it. You know, that if that mean is true, the probability of me getting a sample of 13 or 14, so that should be 14.0. Sorry, I know that the real number is 14.0. It's the one I use when I do the calculations. So, like, if the mean is 13.5, and the probability of me getting a sample mean that's either 13, a sample mean of 13 or something more extreme, is actually less than 2%. Okay? I mean, the probability of me getting one that's like 13 or less is less than 1%, but the probability of me getting even being off by getting a sample that's off by half an inch in either direction, the sample mean is off by half an inch in either direction, is you know, even 2.2% of like finding one that's that way. So I should pretty much not trust that mean. We're going to spend some time on this in class because this is like a complicated and convoluted thing, and we're going to kind of get it down to a structure where you can kind of follow a set of rules without having to think it through. But every so often the AP exam kind of lifts the hood a little and asks you a question to make sure you understand what's going on here. So we'll kind of talk about it both ways. Okay? So we'll see you in class soon.